Hi, everybody, and welcome back to MTED110. Today we're doing lecture 8, and actually what you're going to see is this is a very short lecture. There's only like 9 slides. The reason is that most of the work for this particular chapter, chapter 8, we've already done in previous chapters. So it's kind of putting a bunch of stuff together, and if you've been following along comfortably, this chapter is kind of a fun one. But let's get started here. Let me pull up the slides. All right, so this chapter is all about multiplicative comparisons and multiplicative reasoning. And let's start with this. In chapter 3, when we were comparing things, quantities, we found the difference of their values, right? That's how we were comparing things, which one was larger. Anytime we want to find how much less or greater one number is than another, we found their difference. But this is from the book right here, this quote. Sometimes we want to compare quantities not by how much larger one is than another, but by how many times as large one is than another. Sometimes we want to say things like, oh, that's twice as large, a third as large, 10 times as large, 20% as large, those types of things. So that's a multiplicative comparison. That's the difference that we're going to explore in this chapter. So here's an example, and this will be a good time for you to pause and think and then talk about what you're thinking about. So let's say 2 trees are planted and we compare their growth after a year. One tree grew from 2 feet to 4 feet, and the second tree grew from 3 feet to 5 feet. Which one grew the most? So take a moment and think about that. Okay, and now take a moment and say out loud what you were thinking. Remember, you can talk to yourself, you can talk to a ghost, you can talk to the wall, the ceiling. Hopefully you're talking to your group members and you're watching this together because it makes it even more fun. All right, so let's look at this here. This is interesting because one of the things you'll notice right away is that both trees grew by 2 feet. So notice this tree grew from 2 feet to 4 feet, and this tree grew from 3 feet to 5 feet. And so they both grew the same amount if you look at their difference, right? That's what I'm saying right here. Each tree grew 3 feet. Or I'm sorry, each tree grew 2 feet. But here's the thing. The first tree doubled in size. You see that? It went from 2 feet to 4 feet, so it doubled in size. It's now twice as tall as it was than last year. But the second tree did not. It didn't double its size, right? Because it went from 3 to 5 feet. So if it had doubled, it would have been it would have been 6 feet, right? So it actually increased by a factor of 1 2/3. So basically, if you took that tree last year when it was 3 feet tall and you multiplied that height by 1 2/3, you would get 5, and that's how much it grew. So with this type of a comparison, we can see that the first tree grew the most. So it depends on what type of comparison we want to do. All right. So here's the definition. If you're given 2 quantities, whenever we want to determine how many times as large one of them is than the other one, we do a multiplicative comparison of the 2 quantities. Again, just take a moment and honestly just think about this definition. And I want you to say this definition out loud several times because the wording of it is, what's the word? The wording of it is cumbersome in the beginning. It's hard to hold. You're kind of like, wait, what's going on? Like as large as, many times as. So just take a minute and read this many times and say it out loud several times. Okay, let's continue. The part that I highlighted is usually the part that's the hardest to wrap your head around. How many times as large as this, then the other? We'll see. Okay, so here's an example. Here's another example. A city is expected to grow from 100,000 people to 125,000 people. By saying that the population will grow by 25,000 people, right here, we're doing an additive comparison. So if we say the population is going to increase by 25,000 people, we're saying that you're going to add 25,000 more people to the current population, and that'll give you the new population. In contrast, let me get a different color here. We'll go with this. In contrast, we can also say this. We can say that the population will become 1 1/4 of its current amount. So in other words, if you take the current amount, or sorry, the current population, 100,000, and you multiply it by 1 1/4, then you're going to get the new population. So that's another way of looking at this growth and comparing it, right? So maybe 25,000 people isn't exactly what we care about. Maybe what we care about is basically the growth factor, right? How much is it growing by? That's the idea. So here's the next question. By what percent of the current population is the population expected to grow? So go ahead and take a moment, think about that, and see if you can figure it out. Hmm. Okay, let's check it out and do it together. Let me erase all this stuff. So we want to know by what percent, let me highlight this here, by what percent of the current population, you see that? You see, remember last time from the previous lectures and the previous chapters, I was always like, oh, anytime anybody gives you a ratio or a percent, you always ask of what? Well, we're talking about of the current population. So by what percent of the current population is the population expected to grow? So we know that the population is going to increase by 25,000 people. And what we need to know is what percent of the current population that is, right? I'm sorry. Oh, yeah, yeah. So what percent of the current population that is? Let me see. Did I fill that out here? Did I? I guess I did. Okay. We'll do it right here then. Let's see. What percent of the current population is the population expected to grow? Well, what percent of 100,000 is 25,000? I don't know. What percent of 100,000 is 25,000? Well, one way we could do that is we could use what we learned in the previous chapter and just ask ourselves how many times 25,000 goes in there? How many times does 25,000 go into 100,000? Well, let's check. 25,000, 50,000, 75,000, 100,000. It goes in there 4 times. So that tells us that the population is going to grow by 25%, right? The population is going to grow by 25%. So that's our answer. And we'll write it as a sentence too, just to be absolutely clear. See, this is one of those times where you don't want to just throw out a number like 25%, 125%. Like, it's going to be confusing. You have to be very explicit and say something like, whoa, that's a big pen size. Let's make that smaller. Okay. All right, here we go. The population will grow by 25% of what? Of what, right? Of the current population. 100,000. So there you go. That's how you would do that type of multiplicative comparison. All right. And I'll say this, and I'll say this a couple times in the collaboration meetings too. On the homework for this chapter, virtually every single problem can be solved using a strip diagram, and we're going to see that in a minute here. The other thing I was going to say is the problems in this particular section, you might be tempted to solve algebraically, but try not to. Try to use a method that your students are going to know, because your students aren't going to know algebra at this level. They can do these problems without algebra. Okay, that's just an extra slide. Okay, look at this example. A fifth grade teacher posed the following problem to her students. She said this. Let's read this one together. Jackie invested $20 in a bank, and 3 months later, she received $40 back. Jolanda invested $10 in her bank, and 3 months later, she received $30 back. Which bank would you use? So the students said that it wouldn't matter. Why do you think they said that? Which bank is the better deal? Think about it for a minute. All right, now talk out loud about what you were thinking. Say something out loud. Why do you think they said that? Why would the student say it doesn't matter? Hmm. Okay, and now let's talk about it together. Their students, or her students, probably said that because they're doing an additive comparison, right? Look, she received $40 back after investing 20, $20 increase, right? Oh, she received $30 back after investing 10, a $20 increase. So it doesn't matter, right? Both banks are the same and you're going to make the same. But not quite, right? Which bank is the better deal? Well, let's do a multiplicative comparison and see the difference. See the difference between an additive comparison and a multiplicative comparison. So check this out. She invested $20 in, or Jackie invested $20 in her bank and doubled her money, right? But Jolanda invested $10 in her bank and tripled her money. She got 30 bucks back. So the Jolanda, her bank is offering the better deal because she tripled her money in the exact same amount of time that Jackie did as well. That's an important thing to keep in mind too. You got to make sure that the actual timeline in this case is the same. Otherwise, you have to do some you have to do some changing of units, right? Or sometimes that's called dimensional analysis. That's the fancy name for converting between units, dimensional analysis, if you want to sound really fancy. Anyway, so this just illustrates that people often don't realize that there is a distinction between an additive comparison and a multiplicative comparison. And depending on what you're interested in determines on which one you care about, right? If you're interested in a growth or decay factor, you want to do a multiplicative comparison. If you're just interested in a growth or decay amount, then you would do an additive comparison. Okay. So here's a definition. This is an important definition to know, so make sure you've got this one memorized. It says this: the result of comparing two quantities multiplicatively is a ratio. So if x and y are quantities, then the ratio, written like this, uh, tells us how many times as large x is as y. So we're gonna ponder this for just a few minutes here. But the one thing I want to emphasize is that the symbol that I've highlighted there, the x colon y, that symbol is identical in meaning to this symbol, x over y. You can almost think about it as x per y. That's literally what it is, x per y, and that's what a ratio is. So these two symbols that I've highlighted are interchangeable. Just keep that in mind, and it can help out a lot in this particular chapter and the next one now that I think about it. So what this number tells us, x over y, is it tells us how many times as large x is when compared to y. That's what that sentence means. And then, this is just a pronunciation bit here. We usually say x colon y. We pronounce x colon y as x2y. But I want you to just like ponder this for a minute. So take a moment and reread this definition. In particular, reread the part that I highlighted here. How many times as large x is as y. I want you to read that out loud to yourself about maybe like 5 or 6 times, okay? So just do that right now and take a few minutes. Make sense of that. Okay, and now let's move on. All right, so here's an example, and this is the first time we're going to use a strip diagram to solve this problem. And you'll see what I mean about you might feel a temptation to immediately resort to algebra to do these problems. And I need you to fight that temptation because the purpose of this course, MTED 110, is not to just repeat what you learned back in your K-12 education, right? It's not to just repeat algebra. It's to realize that we can make sense of these problems without such advanced tools. We can make sense of these problems with simple things like manipulatives, Cuisenaire rods, pattern blocks, strip diagrams. Those are the tools that your students have. And then once they are really, really comfortable with those tools, then they transition into using algebra instead. And then what happens is they continue on and then they can go back and forth and back and forth. And that's where the knowledge comes from right there. All right, let's see what we got here. A $120,000 estate was sold and the money was split among two children and two grandchildren. The two grandchildren get the same amount of money and each child gets 2 times as much as each grandchild. See, there's that multiplicative comparison right there. How much did each child get? So we're trying to find out how much each child gets. And let's go ahead and pick out the information we know. We know that the total amount of money we're dealing with is $120,000, and it's split among two children and two grandchildren. But we also know this, each child gets 2 times as much as each grandchild. So each grandchild is getting half as much as their parents, you could say. So how could we do this? Now, again, you might be tempted to go straight to like, oh, 2x plus 2x equals 120,000 and blah, blah, blah. Avoid that. Let's do a strip diagram. If we're talking about $120,000 and we're trying to figure out how to divide it up, let's just pick a strip that's going to represent $120,000, like so. I'll do it down here. Okay, maybe I can turn that a little bit to make it a little prettier. Okay, so this strip right here is going to represent the $120,000. Now it's going to be split up between 4 people, but it says here that the two grandchildren get the same amount, and each child gets twice as much as each grandchild. Okay, so let's think about that here. Uh, each child gets twice as much as each grandchild. I'm going to go off to the side and do a scratch diagram really quick. If this is how much money each child gets, then I know a grandchild would get half of that. It would get like half of that amount. Maybe I'll say that's GC. So this is the kind of structure we're trying to build. And now that I know that this is how much a grandchild would get, I'm just going to kind of like put this next to itself here, put this next to that. Okay. And then I'm going to have 2 sets of that because there's 2 children and there's 2 grandchildren. So I can kind of like see that I'm going to get 2 of those things. So I'll just duplicate it right here. So this is kind of the structure we're looking at, and that should fill up the 120,000, right? So if we're going to do that, then we have to be a little bit more precise because the answer isn't coming out from me just putting these random blocks all over the place, right? But what we need to do is the same thing we did in the past when we dealt with division. We need to find a common unit, or I should say a common sized piece. Maybe that makes more sense. A common sized piece. Well, we can do that because the grandchildren can kind of act as the smallest amount, or I should say the amount of money they're getting can act as our smallest chunk. And we can think about it like this. So I'm going to use a different color here and go like this. Doot, 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 doot. I just divided up the children's portion because I know that this is how much a grandchild gets, for example. And that's really what we needed. We just needed a way to actually compare visually the grandchildren's amount of money and the children's amount of money. And then now we can finally see how we're going to do this with 120,000. So notice how many pieces we've cut this into, and they're equal sized now. They are equal sized pieces. 1, 2, 3, 4, 5, 6, it looks like. So we need to cut $120,000, the strip, into 6 equal sized pieces. Let's do that. Okay. I'll cut it in half first, and then I'll cut each of these into thirds. Notice how this is actually quite precise, right? They have to look just about the same size. It doesn't have to be perfect, but they shouldn't be all over the place, right? And now what we're going to do is this. Okay, so if we take $120,000 and we divide it by 6, how much does each one of those blocks represent? What do you think? Let's see, what's 120,000 divided by 6? What's 12 divided by 6? 2, right? So I think these are what, 6,000 each? I think it's 6,000. So I'm going to say 6K, 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 6K. Is that right? Hmm. 6 times 6. No, that's not right. Doesn't make any sense, right? That's how we can catch ourselves. What is it? 20K? 20K? That'll give us 40K. That'll give us 60K, which is exactly right, right? Because now I've seen half of that, and half of that is 60,000. Whew, good thing I caught myself. Okay, so that's how much each one of those blocks represents. And now, based on our scratch work that we did up here, we know that this would be the amount that a child gets, and this would be the amount the other child gets, and then these will be the amount the 2 grandchildren get. 40K, 40K, 20K, 20K. And now what I'm going to do is I'm going to go over here off to the side and I'm just going to answer the question. How much did each child get? See, this is where you have to look back, right? You don't want to just dust your hands. My strip diagram looks so pretty. I'm ready to go out. See ya. No, you got to stop and look back. So let's do that. Each child got $40,000. Boom. And that's the answer. So again, notice that I didn't bring in any sort of variables per se. I didn't bring in any sort of algebraic manipulation or solving for x. We were actually, quote unquote, solving for x in this problem, but we didn't introduce any of that advanced algebraic stuff, any of those advanced algebraic notions or symbols or notations. We just use a strip diagram. And again, strip diagrams are great because you can also model them physically. You can model them with linking cubes. You can model them with Cuisenaire rods, which I don't have on me. So it gives your students a really robust way of exploring these things. Okay, let's do this one. This is a fun one. And actually your activity is basically doing a bunch of these to get practice with these strip diagrams. So a candy bar is going to be shared among two people. Draw a diagram that models the following comparison and answer the related questions. Okay, so the first thing we're given here is this. In this candy bar, part A is 4/5 as large as part B. So what that means is if I took B, the length B, and I cut it into 5 pieces, A would be 4 of those pieces. So let's draw a picture here. Actually, let me ask you this. If we can cut B into 5 pieces and A is going to be 4 of those pieces, and we know that the whole candy bar is going to be the amount that A is and the amount that B is, how long or how many pieces should the whole candy bar be? Think about that for a minute. Hmm. Hmm. All right, now let's do it together. It's going to be 9 pieces, right? And I'll show you why. Let's draw our strip diagram. I'm going to cut it into 9 equal-sized pieces. Wish me luck here. 1, 2, 3, 4, 5, 6, 7. Oh, not quite. 8. There we go. 9 equal-sized pieces. Okay, so here's the idea. Part A is 4/5 as large as part B. So what I'm going to go do here is I'm going to highlight part B. Part B is 5 of these pieces. So that's right around here, okay? This is part B in blue. There we go. And maybe I'll even just indicate that this is actually B. And then part A is 4/5 as large as part B. So part A is going to be 4 of these pieces. Boom. And that's what we needed. So now this is a picture of the entire candy bar, and that's the key idea. So now we have the total candy bar, and we have the exact representation of A and how it compares to B. So everything's good, and now we can proceed by answering the questions, or we can proceed with answering the questions. So the first question says, part B is how many times as large as part A? Okay, let's think about this. Part B is how many times as large as part A? So in other words, if you took part A, let me circle it here. If you took part A and had to multiply it by something so that you got B, what would you have to multiply it by? Well, take a look. A has 4 pieces and B has 5. So we're going to need at least one whole A, but then we're also going to need a quarter of an A. Yeah, 1/4 of what, right? Of what, of what, of what? We need 1 1/4 lengths A to make the length B. So think about that for a minute. So ponder that. Yeah, we need 1 1/4 lengths A to get the length B. And I hope that you can see that in the picture there, right? A is 4 pieces, and if we needed 5 of those pieces, that would be 1 1/4. There we go. Okay, so the answer to the first question is 1 1/4. The second part says, how much of the bar is part A? And here is the catch, right? Notice the referent unit has changed. Up here in part I, in part I, we were comparing B to A, right? I'm sorry, we were comparing A to B. So our referent unit was different. Our referent unit was A. We said we needed 1A and then 1/4 of an A. Now in this second question, II here, the referent unit has changed. We're referring to a different unit for this question. The unit in this question is the entire bar. And the question says, how much of the entire bar is part A? Well, we can see here that the answer is 4/9. A is 4/9 of the entire bar. There we go, 4/9 of the entire bar. And then part 3 here, I says, what is the ratio of part B to part A? So now we're changing the referent unit again. We're comparing B to A. What's the ratio of B to A? It's 5/4. It's 5/4. So the answer to that one is 5:4, right? Remember, this is the same thing as saying 5:4, and we wanted to know what's the ratio of B to A. There we go. So the ratio of B to A is 5:4, which is 5/4. There you go. Okay, so that's it. That's it for the entire thing. I'll pull up the activity here so you can take a look. But the activity is just doing that several times. So it's the same question. Candy bar is to be shared among 2 people. And I just want you to practice with these things. Practice drawing these bars out and so on. And it's just a bunch of those. That's really all it is, okay? And that's pretty much it. So yeah, let me go ahead and I guess I'll say good night and I'll see you in the next lecture. Sometimes they're just so short, you know what I mean? All right, have a good one.